So hello everyone, I'm going to introduce the speaker of today's presentation. His name is Jean-Flavien, who is a PhD student at Eurocom, and he and I work on the same project, which is called Attention, with Paolo Papotti, who is present here today also. And the main purpose of this project is to fight against online disinformation. It is a large ANR project with a lot of institutes involved, like the University Paris 1, CNRS, and also some startups like Basta AI. So basically, this project has several modules, and I work mainly on the counter-argument generation, and the work of Jean-Flavien is the module before the mine, so he works on the fact-checker module, whose main purpose is to detect fake news, let's say. So Jean-Flavien, the floor is yours.
Thank you. So, hi everyone. Today I will present you the work we did on fake news detection about generating training example for natural language inference and tabular natural language inference models. So this is a work we did in the context of the NLI Attention project with Serena and Elena. So let me first introduce the problem of fact-checking. So we have this dataset that we use, which is called Feverous, containing hard manually curated text and tables. It contains both text and tables. And so each examples contain a claim, the evidence to support or refute the claim, and of course, the verdict for such claim. So for instance, here we have the claim, Red Sundown Screenplay was written by Martin Berkeley, based on a story by Lewis B. Patten, who often published under the names Lewis Ford, Lee Litton, and Joseph Wayne. To check this claim, we see that in the table of evidence, we have Martin Berkeley Screenplay by, based on Lewis B. Patten, which we find in the claim. And in the page, we find the sentence he often published under the name Lewis Ford, Lee Layton, and Joseph Wayne. Both this tabular and textual evidence is used to verify the claim. And of course, we have this verdict, which is supported in that case. So in fact, the dataset is composed of 87,000 manually annotated claims like this, because the best methods are based on machine learning, and there is, so of course, a need for training data. But it's expensive to write, it's slow to create, and of course also it's prone to errors. So the outline, I will present first the problem overview, and then I will show three kinds of approach that we took to solve this problem. So the first kind, with the paper TNET, is about generating claims using structured data. And the second and third kinds are about generating claims using both structured and unstructured data. Finally, I will conclude and present some future works. So, first of all, on a fact-checking model, there is this pipeline. So here again, we have this same example about Red Sundown. So given the textual claim C at inference time, the claim will pass in a retriever that will give the relevant evidence for the claim, and a predictor that, using the claim and the evidence, will predict a label for it. So either support, refute, or not enough information. Those are two supervised models. And we assume that, of course, the corpus of example is clean. So I presented inference time. Now I will talk about the training time. So at training time, we have those examples for training. So as we saw, each example containing claim, evidence, and label. And that are based on the corpus. In the Feverous case, it's a Wikipedia page. And then they are used as input to train the models for fact-checking. So that are supervised models that we saw. There were two models. First, the retriever, and second, the predictor. So we see that those examples for training are needed to obtain a functional fact-checking pipeline. So As input, we have a corpus, as we saw, and the problem is that the manual writing of the training set is costly. We may wonder how to generate a training set using low human intervention. The solution proposed is to build new examples with new evidence. We focus on data-driven AI. So we focus on how to improve results using better data rather than changing the model. So about example generation, many methods exist to augment existing examples, but it differs from what we want to do. Why? Because augmenting examples, we think it's insufficient for variety. For instance, an augmentation could be read for, so let's take again this claim, Red Sundown Screenplay was written by Martin Berkeley. By augmenting, we could get something like Red Sundown Screenplay was authored by Martin Berkeley. So those examples are good, of course, but we want more kind of variations. This brings us 3 challenges. The first one is automation. So how to avoid manual work and to be scalable. We want the best variety in data patterns. And of course, we want the claims to have the most human-like language possible. So to solve this issue, we took 3 kinds of generation. First is tabular only. So it's the paper named TNet, and that's about tabular natural language inference. So it's to check the inference of a textual statement using a table as premise instead of text. So it was an unexplored problem previously. And then we went on the text evidence. So there was already some tentative. And finally, we went on the table+text setting. So we mixed both kind of data. And those are new experiments. And we think it's mandatory to capture the full meaning of data. We were inspired by the multi-modality of Feverous examples to do this. So now that we saw the fact-checking pipeline, let's see the example generation pipeline. So at the beginning, we have a document, and from it, we can take either the table or the text or both into an evidence selection module. This evidence selection module will take from the page evidence using various strategies such as random or other strategy that we call warm start and that I will present later on, before giving those evidence to a claim generation module that can rely on several models to generate new training examples. So let's see an example. Here we have this document. It contains a table with name of cities, their superficie, the number of inhabitants, and the country it's in, and several sentences. So here the Coliseum is in Rome, sorry. Nice is a city close to the sea. Toulouse is known for chocolatine. And so the title of the page could be tourist cities. So first of all, we go to the evidence selection module, and we select from the page random evidence. And so we have the selected evidence in red here. Before going to the claim generation, where using those evidence, we obtain a claim, for instance, the positive claim case, Rome, which is known for the Coliseum, is 1,000 square kilometers and has 2 million inhabitants. Or a negative claim, Rome, which is known for the Tour Eiffel, is 1,000 square kilometers and has 30,000 inhabitants. And from it, we obtain a new output example that can be used either for training or testing. So this brings us 3 challenges. The first challenge is about evidence selection. So we saw this table and this sentence, how to select in the best way possible the evidence. So we have this first box, which is kind of a relevant selection, but then we have also this one with weird tabular evidence selection. Also this one with a different number of, and also how to choose the number of evidence to choose. The second challenge is the variety of claims. So it's important for better training of the model. We don't want a template-based claim. So for example, here, using the same table, we could have Rome is 1,000 square kilometers, Nice is 72 square kilometers, Rome is 2 million inhabitants, etc. And so it wouldn't give the best training for the model. We want a richer approach, like having claims like Rome is 1,000 square kilometers and has 2 million inhabitants, Nice is smaller than Rome, Monaco is the smallest city among tourist cities, etc. So then the third challenge is negating claim. Given those evidence, we want to get negative evidence. So for example, here for the same table, we can have the possible positive claim. Rome, which is known for the Coliseum, is 1,000 square kilometers and has 2 million inhabitants that we just saw. And we could get as negative Rome, which is known for the Tour Eiffel, is 1,000 square kilometers and has 30,000 inhabitants that we also saw. Rome, which is known for the Berlin Wall, is 1,000 square kilometers. Rome, which is not known for the Coliseum, is 1,000 square kilometers. So this is simple negation. So how to generate those negative examples? Sorry. So we have two pipelines. The generation pipeline, as I just presented, and the fact-checking pipeline that I presented earlier. Our contribution focuses on the generation pipeline. So to start with, the first part of the pie, the generation using tabular evidence. In this context, we have as input tables, and we generate claims from tabular evidence. So it's, as I mentioned, TNLI, and the motivation is that it's an unexplored path. Nobody tried to generate TNLI examples from table, and we believe a lot of knowledge present in tables only is not exploited. So how are we going to do this? We want to convert tabular data into textual claim. So for instance, here is a case of tabular evidence-based claim. Using those same evidence, we have Rome 1,000 square kilometers and Nice 72 square kilometers selected as evidence that are in red. And we obtain from this the claim Rome is larger than Nice, that is label support. We saw in the generation pipeline, the first step is evidence selection. So here I will start by the cold start. And let's assume that we have this table with name, age, city, and country of French researcher. So we could have various evidence selection. So we could take randomly those four cells, obtaining Paolo 40, Lore 20. Those four cells, obtaining Paolo 40, France, France. Those four cells, so Paolo 40 Nice France, which is a complete row, and this one, which is Paolo 20 Nice France with a 20 as a little bit an outlier. So as we can see, using random selection, we get relevant selection sometimes, but also less relevant selection. That's also why we wanted to have the warm start. So as we don't want to have basic templates, neither evidence with no sense. So we try to inspire from human to get very high quality examples. So we believe that those examples are needed to create complex claims that are not just lookup, because to be able to compare between the evidence selected, you have to have a coherence. So let's explain this. Let's assume we have this same table as before, but a little bit expanded with two more rows. So that was present in the original corpus. We have Paolo and Lore are from France as the original claim, and with the four evidence selected, Paolo, Lore, France, France. From those four evidence, we generate a graph where we put as node each cell and as edge the relation between the cells, the evidence cells. From this, we generate a query that will give us, as a result, 4 possible claims in this table, respecting the same pattern as the human did, but with different evidence selection. So you may wonder why we want to derive from the human example and not directly from the claim and do semantic parsing. So semantic parsing is the task of transducing natural language iterants into a formal meaning representation. So here, for instance, we have this table with the question, who is the oldest researcher, on the same table as before. Giving this claim, the semantic parsing model should give an output query like select name, max age from table to give the oldest researcher. So why don't we use it instead of our pattern-based approach? So because first, the Wikipedia page, table format can be inconsistent because there are entity tables and relational tables, and also the type of data present inside them is also inconsistent. Second of all, the semantic parsing the dataset use question as input while we have claims. And finally, it generates a query designed to return a single result while we want multiple results to build new claims. So we tried it anyway using the state-of-the-art RAT SQL model, but it couldn't produce any relevant queries. So now that we are done with the evidence selection, I will go on the next part of the pipeline, which is the claim generation. I will start by the support side, so generating positive claims. So given again the same table, we have multiple interpretation of those same evidence. So we could do a simple lookup. Paolo is 40 years old and Laura is 20 years old. We could do maximum and minimum. Paolo is the oldest researcher. Laura is the youngest researcher. We could do a count. There are two French researchers. Compare Paolo is older than Laura, etc. So my motivation is that the state of the art is using T5 fine-tuned on Toto. So Toto is a table-to-text dataset, but this T5 can only generate lookup examples, which are like as shown with the example Paolo is 40 and Laura is 20. It's just the description of what you can see. And it's not enough for having the best variety as we wanted. So we want to find what are the possible type of claim that we can produce. How to detect the possible type of claim to produce? So we want to, given the evidence, to get the query, to see what are the query queue, such as given the data D, so the data D is the entire table, we get that the query applied on D gives us the evidence. So we call it SQuery. There are two types of SQuery, the local SQuery, which only require having the selected evidence, so the red ones here, or a global SQuery that require to have a look at the entire table to get an answer. So filter or max minimum, because of course to do this you need to check that it's indeed the minimum or maximum, for instance. Examples of that are if you take this table, so can we do a filter on the age under 22? So the selected, yes, it's possible here because all the selected evidence are under 22, age under 22, sorry, and the remaining one is over. So it's a possible interpretation of evidence, and we could build, for example, the claim, all researchers in Eurocom are 20 years old or less. Can we do a filter on city equals New York? So yes, for the same reason. So a researcher in Eurocom lives in New York. Then, as I mentioned, the lookup, which don't need the other data, and you could do one researcher is 22, one is 19, one is 18. They live in New York and work in a team DMS. Then you could do also comparison using only the selected data and is older than John. And can we do a filter team equals DBMS? No, this is not possible because, as you can see, outside the selected evidence, we have another researcher that is in the team, but not selected as evidence. So now that we saw the positive side of generation, let me introduce the negative side. So the refute side. Injecting error is not obvious. So how do we do this? We start from the table. So that was Paolo 40, Nice, France, Laure 20, Paris, France. And as you can see, we shuffled a colon, so the colon age, plus we appended a new row using false tuple injection to get a table that will give fake claims in any situation. So there are still many possible interpretations. So for example, the lookup would become Paulo is 20 and Laure is 40. Maximum minimum would be Laure is the oldest researcher, Paulo is the youngest researcher. Count now would be there are 3 researchers thanks to the new row added. And compare would be Paulo is younger than Laure. So from this table, we extract the evidence to build those kind of claims. But of course, at inference time on the fact-checking pipeline, we will use the original evidence that we saw before to see that, in fact, the claim is refuted by the data. I presented the negative example generation for the cold side. Let's see now for the warm side. So that was the continuation of what I presented with the query previously. So as you saw previously, we have this table of results from the query, given us 4 possible claims to produce. So the positive pipeline would give us, for instance, this, as we saw. And for the negative pipeline, now, how do we generate a negative example in this case? So in that case, we shuffle among the results of possible claims and in a kind of similar process. So we obtain a false table of results that will be false in any interpretation, also still with false tuple injection. We tried our method in several settings, so I will present some results on the Feverous dataset on table-only setting, of course, and we will see how their claims, the human-generated claim, claims compare with our generated one. On this table, you have on the y-axis the inference accuracy on the fact-checking pipeline, and on the x-axis, you have the number of training tables that were given to train the fact-checking pipeline. So you have 4 models in comparison. The one trained with our warm start, TNetW, so the query approach I introduced. The cold approach, which was with random evidence selection, which is TNetC. Then we have the model trained with the human data. And then we have the model trained with human plus augmented data. So human plus augmented means that we took the human claims and also augmented them using 7 augmentation techniques. As we can see in the table, even with a low number of training tables, our both TNet approach produce high accuracy before getting equalized with a human that does even better in the end. You have to mention still that we generate multiple examples for a single table, while the human produced only one. So this is a little difference. We tried our technique on other datasets, so info tabs and TabFact. So here again, a graph of results with on the left side the results on info tabs, and on the right side the results on TabFact. The y-axis is still the inference accuracy, and we see that so on the left side the human does way better than we do with our approach. This is because InfoTabs is a model-based, dataset based only on entity tables, while we design TNet mostly to work on relational table. So what is an entity table? An entity table is like a relational table, except it's transposed, and each attribute has only one cell. On the right part of the graph, we have the TabFact results, and we see that here we are doing quite close to human. I will switch to the second side of the pie, which is example using generation using textual evidence. So this time as input we have text. So we generate claims from textual evidence. There were already some works on this, but we believe it is possible to do better and to do more generic, than approach that use knowledge base. So here is an example using only textual evidence. So you have those two evidence. Rome is in Italy. Italy and France are two countries. Based on those two evidence, you can obtain the claim Rome is not in France, and the label is support. So the state-of-the-art technique that I just mentioned is the using a knowledge base. We first generate a positive claim, and then we use entity replacement to generate negative ones. We don't have a knowledge graph here. So what we do is that we use GenSim, ConceptNet, and Flantify to select entities to replace and also to replace them. And we tried different techniques to select the right entity to replace. But the best accuracy we obtained in the end was 0.77, which is far from the 0.95 of the original training data, and also far from what we got with our technique. So for instance, here is an example of entity replacement. Let's say we have the claim Coca-Cola is an American brand. You select the entity American, you replace it with Australian, and you obtain Coca-Cola is an Australian brand. Which is, of course, we go from a support label to a refute label. So how do we want to generate those examples? We want to use text summarization technique, which is generative summarization. It brings us two challenges. First, how to select the evidence to use for the claim generation. And second, also how to negate claims. So it was quite simple in the case of tabular evidence, as we saw with the shuffling. But here, how to deal with the text-only setting. As always, for the generation pipeline, we start by selecting the evidence. What is the best strategy to select the evidence? So we tried four techniques. The first three use the best score obtained with BERT score and Rouge to select evidence, and the fourth one use simple random selection. So using those the selected evidence using those four techniques, each time we construct claims using BERT large, and then we test those claims on the fact-checking pipeline to get the accuracy that we obtain in the table. And we see that in the end, random selection wins. So that is the strategy for evidence selection that we keep. So now we go to this generation side. There are two family of methods. So we have two strategies. First is the strategy of using a tiny model like BERT large, or using a large language model. Then this used as they are is our cold approach, because we don't require any human data. But we can also improve those models by using an optional fine-tuning on low percentage of the current dataset for the tiny model. And for the large language model, we can use a few-shot approach using adding some examples to the prompt. So for both cases in the warm approach, we require example from the dataset we are going to use. We implemented our method in several ways, and we test it. And so we obtain this graph, so that I will introduce and present. So in this graph, we have, as always, the accuracy on the fact-checking pipeline. And on the x-axis, you have the number of training samples used for fine-tuning the generation model. So 0 is our cold approach, in fact. And 10K, so we is using a 10K example from the dataset, which is kind of unrealistic, but is just to show our upper bound. And we see that training our model with only 100 examples from the target dataset, you obtain already very similar results to using the full dataset. And so we also compared 3 kind of negative generation. So we have BART, BART plus BART-neg, and BART-neg. So BART is a BART-large model that we fine-tune or not. BART plus BART-neg means that for the negative example, we first generate a positive claim using BART-large, and then we negate it using BART-neg. And finally, we have the BART-neg approach where we just use BART-neg. So BART-neg is a BART-based model tuned on Wikipedia negative data. We also tried our model on SciFact, and we see that our cold and warm get satisfying results compared to original. So SciFact is a scientific data set, and it's the one that was used for the state-of-the-art technique. Finally, the most general case, which is generation using both tabular and textual evidence. So as input, this time we have text and table, and we generate claims from tables and textual data evidence. Sorry. So the motivation is that it's an unexplored path. We think that text or data alone is not enough to capture the full meaning of the data, and there is a need to mix textual and tabular evidence. So how are we planning to do this? We want to mix our 2 approaches. This brings us 2 challenges. So first, how to select the evidence, of course, as previously. So how to select the sentence and table evidence. Is random selection of evidence still a good option here? And then the second challenge is how to mix those 2 types of evidence that for the claim generation. So for challenge 1, let's take this table and sentences as example. So we have this table with 3 rows and the name, city, and age of people, and those 5 sentences. So here we have the selected evidence Paulo Rome 42, and we have those 5 sentences. So how do we select among those 5 sentences the ones that are satisfying? So either we can do random selection. So for instance, we could take pineapple pizza is popular, Obama was born in the US. And we could also use smarter approach using semantic consistency. Taking those 3 cells, we see that Rome is in Italy and Italy is near France are 2 good candidates to go with the cell selected. So as always in the generation pipeline, we start by the evidence selection. So we have the input table and sentences. We go through one of the strategies, so random evidence selection or semantic consistency that I just showed, or taking the original evidence, and we get the resulting selected evidence. Then we want to go on the generation part, and that brings us to our second challenge. So how to mix evidence. So to do this, we convert the cellular evidence into claim using our pipeline for claim generation. That was the first kind of generation that I presented of TNet. And then we use the table as standard textual evidence. So as you can see here, those 4 cells were selected here because they are in red. Red is evidence, blue is data, and purple is a language model. So taking those 4 selected cells, you go through the pre-trained language model of the first kind, which can be T5 fine-tuned and Toto. So why do we use T5 fine-tuned and Toto here while I mentioned that it's only produced lookup claims? Because for this type of claim generation, we believe it's good enough because it's just to describe the evidence selected in order to convert it inside a textual claim. So given those 4 cells, we convert it into textual claim, and then we are back to the second kind of generation problem where we go from textual evidence to the output claim directly, so using the BART large that we saw in the second part. And of course, we use the best model from the second part to do this generation. So we ran the experiments on various data, and we obtain those results. So using original data, and so with original evidence selection, of course, we obtain an accuracy on the fact-checking model of 0.82. But we see that with our approach using Bartlarge and Bartneg and warm approach, so meaning that we took examples for fine-tuning the Bartlarge and Bartneg, we see that we go up to an accuracy of 0.87, while entity replacement only went up to 0.84. We also tried with large language model to compare with, so and we see that we got between 0.81 and 0.84. So those experiments were all run on the same setting with 3,000 examples on the Feverous dataset. In conclusion, we can say that we proved the potential of example generation to train model in the textual setting, in tabular setting, and also in the combination of both. And it can be of great help when we have time constraints or lacking data. As a future work, we want to use various prompts to increase diversity of the claim even more. And also we want to be able to deal of not enough information labels, which is a small fragment of the original dataset, but that we kept aside for now. Sorry.
Thank you very much.